What if everything you thought you knew about the universe was just the tip of an unimaginable iceberg? Picture standing in a room, convinced you're seeing all there is. But behind the walls, above the ceiling, woven into the very air around you, lie hidden dimensions, curled up so tightly they escape even the most advanced instruments. This isn't science fiction. It's one of the most profound ideas in modern physics. String theory's proposal of up to 30 unseen dimensions, each shaping reality in ways that defy our everyday experience. For centuries, we've lived under the illusion that space is flat, predictable, limited to length, width, and height. But what if those 3 dimensions are just the beginning of a far grander story? Think of the universe as a cosmic symphony, where every particle, every force, even the fabric of spacetime itself, vibrates like the strings of an instrument. String theory suggests these vibrations aren't just metaphors. They're the building blocks of everything, playing out across dimensions we can't perceive. Some of these dimensions might be curled into shapes smaller than an atom, while others could stretch endlessly, parallel to our own. Imagine a spider's web glistening with dew, except each droplet is its own universe, connected by threads of higher dimensional space. The implications are staggering. Black holes might not be the end of matter, but gateways to these hidden realms. The Big Bang, perhaps just a collision between dimensions, and the laws of physics as we know them, merely shadows of a deeper, more intricate truth. This isn't just about abstract equations or far-out speculation. It's about rewriting the very definition of reality. For the first time in history, we're on the verge of glimpsing what lies beyond the limits of human perception. Over the course of this journey, we'll unravel how these extra dimensions could solve mysteries that have baffled scientists for decades, from the nature of gravity to the existence of parallel worlds. We'll explore how mathematicians visualize these impossible spaces, and why some physicists believe we're living in a multidimensional hologram. By the end, you won't just understand string theory's bold claims, you'll feel them, like catching the faintest echo of a hidden frequency. So let's dive in, beyond the visible, beyond the familiar, into the extraordinary tapestry of a universe far richer than we ever dreamed. The story of string theory starts not with a grand revelation, but with a curious accident, a mathematical coincidence so striking it couldn't be ignored. In 1968, a young physicist named was sifting through old equations, searching for patterns that might describe the behavior of subatomic particles. What he found was a formula, written decades earlier by the mathematician, that perfectly matched the way particles interacted during high-energy collisions. But here's the twist. His work had nothing to do with physics. It was pure mathematics, a beautiful abstraction. How could this equation, born from the world of numbers, suddenly explain the chaos of quantum particles? The answer would rewrite the rules of reality. His discovery was like finding a key that fit a lock no one knew existed. Other physicists, including, soon realized his formula wasn't just describing point-like particles. It hinted at something far stranger. Imagine plucking a guitar string and hearing a single note. Now imagine that note isn't just sound, but matter itself. Propose that particles might not be dots, but tiny, vibrating loops of energy, each oscillation producing a different particle, an electron. Just one note in the cosmic symphony. A quark, another harmonic. This was the birth of string theory, a vision where the universe's building blocks weren't scattered dots but threads of vibrating energy, weaving the fabric of reality. Yet for years, the idea remained on the fringes. The math was dazzling, but the theory had a glaring flaw. It only worked if the universe had more than the 3 dimensions we experience. To physicists steeped in classical thinking, this seemed absurd until the 1980s, when breakthroughs in supersymmetry revealed a shocking elegance. By adding extra dimensions, strings could unite quantum mechanics and general relativity, 2 frameworks that had stubbornly resisted reconciliation. Picture 2 languages, each describing half of a story. String theory wasn't just translating between them, It was revealing they'd been fragments of a grander narrative all along. What makes string theory so captivating isn't just its ambition, but its sheer audacity. It turns the universe into a multidimensional ballet, where gravity, light, and matter emerge from the dance of strings. And while we've yet to detect these vibrations directly, the mathematics paints a picture too compelling to ignore. One where every law of physics, from the quantum to the cosmic, might just be notes in a hidden harmony. Why would the universe need 30 dimensions when our daily lives play out perfectly well in just 3? The answer isn't found in grand cosmic declarations, but in the quiet language of mathematics, equations so precise they leave no room for debate. String theory's foundation hinges on a delicate balance, one that collapses if confined to the familiar dimensions of length, width, and height. In the early days of the theory, physicists stumbled upon a glaring problem. Their equations only made sense if space had 10 dimensions. Add one more and everything snapped into an even more elegant framework, M theory's 11 dimensions. But here's the catch. These extra dimensions aren't sprawling landscapes like the ones we know. They're tightly wound, curled into shapes so tiny they're hidden from even our most powerful microscopes. Think of it like a garden hose stretched across a field. From a distance, it looks like a simple line, one dimension. But up close, you see its circular surface, a second dimension wrapped so tightly it escapes casual notice. Now imagine that hose isn't just a cylinder but a six-dimensional manifold, a shape so intricate it could fit in a space far smaller than an atom. These hidden folds aren't just mathematical curiosities. They're the reason electrons have mass, why gravity feels weak compared to other forces, and how particles like quarks and neutrinos end up with their distinct properties. Each vibration of a string, each note in the cosmic symphony, is shaped by the way these dimensions twist and intersect. But why not fewer dimensions? Why not 5 or 7? The math is ruthlessly clear. With fewer than 10, the equations of string theory become plagued by anomalies, ghostly terms that refuse to cancel out, rendering the theory inconsistent. It's like trying to balance a pencil on its tip in a gusty wind. The numbers simply won't stay put. But with 10 dimensions, everything aligns, forces unify, quantum jitters smooth out. And when M theory enters the picture, that 11th dimension reveals a shocking possibility. Our universe might be one membrane floating in a higher dimensional expanse, with parallel worlds hovering just out of reach. The real magic lies in how these dimensions solve puzzles that have stumped physicists for generations. Take gravity, for instance. In our three-dimensional world, it's the weakest of the fundamental forces, yet in higher dimensions, it might be as strong as the others. Its apparent feebleness just a side effect of leaking into hidden realms. Or consider the bizarre behavior of quantum particles, which seem to teleport and entangle in ways that defy classical logic. Higher dimensions could be the stage where these phenomena play out, invisible to us but written into the fabric of reality. This isn't wild speculation. It's the inevitable conclusion of following the math where it leads, even when it defies intuition. And while we can't yet peer into these hidden dimensions directly, their fingerprints are everywhere, in the way particles scatter during collisions, in the subtle ripples of spacetime, even in the dark matter that silently shapes galaxies. The universe, it seems, has been whispering its secrets in geometry all along. We're just beginning to learn how to listen. Trying to wrap your head around 30 dimensions is like teaching a goldfish to visualize a thunderstorm. It's not just difficult, it feels almost impossible with the tools we have. But here's the trick, we don't need to see these dimensions to understand them. We just need the right metaphors to bridge the gap between the abstract and the intuitive. Start with something simple, a shadow. A three-dimensional object casts a two-dimensional shadow, a flattened version of itself. Now flip that idea. What if our entire three-dimensional world is just the shadow of a higher dimensional reality? Every movement we make, every object we touch, might be the echo of interactions happening in dimensions we can't perceive. Take a sheet of paper. To a two-dimensional being living on its surface, folding the paper would seem like magic, their flat world suddenly bending in ways they can't explain. For us, folding three-dimensional space is just as baffling, but string theory suggests these folds are everywhere, hidden in shapes smaller than atoms. Imagine a city map crumpled into a ball. From a distance, it looks like a mess, but up close, every street and intersection still exists, just compressed. Higher dimensions could be like that. Every fold influencing how particles move, why gravity behaves the way it does, even how time flows. Video games offer another clue. Ever seen a character glitch through a wall? In their digital world, it's a bug, but in ours, it's proof that their reality is just a limited projection of deeper code. If our universe is a simulation, those glitches might be higher dimensions poking through, like cosmic or particles teleporting in quantum experiments. Even holograms hint at this, a three-dimensional image encoded on a flat surface. Some physicists argue our universe might work the same way, with all the information of higher dimensions printed onto the boundaries of space-time. The real power of these metaphors isn't just in making the math relatable, it's in revealing how limited our perception is. A spider senses vibrations in its web but can't comprehend the hand that plucks it. Are we any different? The vibrations of strings, the folds of hidden dimensions, might be the universe's way of humming a tune we're only beginning to hear. And every metaphor, from crumpled paper to glitching pixels, is another step toward tuning our minds to frequencies beyond the visible. We take the three dimensions of our everyday world for granted. Length, width, and depth seem like the full extent of reality. But time, the fourth dimension, already hints that there's more to the story. It's not just a backdrop, it's woven into the fabric of space-time, bending and stretching under gravity's influence. Yet even this four-dimensional picture might be just the surface. String theory suggests that dimensions 5 through 10, or even more, are curled up so tightly they're invisible to us, like the coiled threads of a rope that appear as a single line from a distance. Imagine blowing up a balloon. To an ant crawling on its surface, the balloon seems flat, two-dimensional, but we know it's actually a three-dimensional sphere. Now take that idea further. What if our entire universe is like that ant's perspective, unaware of higher dimensions folded into the microscopic fabric of reality? This concept, called, turns the extra dimensions of string theory from a mathematical quirk into a potential master key for unlocking physics' greatest mysteries. One compelling idea is that our universe might be a three-dimensional membrane floating in a higher dimensional space called the bulk. Picture a slice of bread in a vast loaf. We're stuck on the slice, oblivious to the loaf's true scale. In this scenario, gravity's puzzling weakness compared to other forces starts to make sense. While electromagnetism and nuclear forces are confined to our brain, gravity could be leaking into the bulk, diluting its strength from our perspective. It's like trying to hear someone whispering in a crowded room. The sound isn't weak, it's just spread thin across dimensions we can't access. The fifth dimension adds another twist. Unlike the tightly wound dimensions 6 through 10, it might exist just beyond our perception, acting as a bridge between parallel. Think of it as a hallway connecting countless rooms, each a separate universe with its own laws of physics. This could explain why gravity behaves so oddly at quantum scales. It's not just a force within our universe, but a ripple echoing through the bulk, touching realities we'll never see. These ideas aren't just mathematical fantasies. They're testable. If extra dimensions exist, particle colliders might someday produce tiny black holes that vanish instantly, their mass evaporating into the bulk. Or gravitational wave detectors could catch anomalies, ripples that don't match predictions, hinting at unseen dimensions warping spacetime in ways we're only beginning to model. The universe has a way of hiding its deepest truths in plain sight, waiting for us to ask the right questions. And if the answers lie beyond the fourth dimension, we're standing on the threshold of a revolution in how we understand reality itself. If the fifth dimension feels like stepping into the unknown, dimensions 6 through 10 are are where reality truly loses its grip on the familiar. These aren't just extra directions you could point to if you had the right eyes. They're the invisible architects of everything, shaping the universe at its most fundamental level. Picture a grand piano where every key produces not just a note, but an entirely different particle. The way those keys are arranged, the spacing, the tension determines whether you get an electron or a quark, a photon or a boson. In string theory, the hidden dimensions are the piano's hidden framework, dictating how strings vibrate and thus what kind of matter or energy they become. At the heart of this lies something called a manifold, a six-dimensional shape so intricate it defies visualization. Think of it as the universe's ultimate origami, folds upon folds, twists within twists, all compressed into a space a billion times smaller than an atom. These shapes aren't arbitrary. They're mathematical masterpieces, fine-tuned to ensure the vibrations of strings produce the exact particles and forces we observe. One subtle kink in the geometry, and electrons might weigh 1,000 times more, or gravity could vanish entirely. It's as if the laws of physics were written in the creases of these hidden dimensions, waiting to be decoded. Here, where it gets even stranger, the way these dimensions curl and intersect doesn't just affect particles, it could explain why the universe looks the way it does. Take the cosmic speed limit, the speed of light. Why that particular number? The answer might lie in how vibrations travel through these higher dimensional labyrinths, constrained by their geometry like sound waves echoing through a cathedral. Or consider dark matter. What if it's not some exotic particle but ordinary matter interacting with dimensions we can't see? The possibilities spiral outward, each more tantalizing than the last. But how do we know any of this is real? The beauty and frustration of string theory is that these dimensions are too small to probe directly, at least for now. Yet their fingerprints are everywhere. Particle colliders like the Large Hadron Collider might one day spot anomalies, tiny deviations in energy or momentum that hint at particles leaking into higher dimensions. Even the fabric of spacetime itself could bear scars from these hidden realms, subtle wrinkles in gravitational waves or light from the early universe. It's detective work on a cosmic scale, piecing together clues from the tiniest particles to the largest structures in the cosmos. What's astonishing is how much rides on these invisible folds. The charge of an electron, the strength of gravity, even the number of dimensions we perceive, all could be accidents of geometry, frozen into place during the universe's first moments. It's humbling to think that everything we see, from swirling galaxies to the screen in front of you, might just be the surface ripple of a deeper, richer reality. And if we're right about these hidden architects, we're not just uncovering new dimensions, we're rewriting the very definition of existence. Just when string theory seemed to settle into 10 dimensions, a seismic shift rocked the foundations of physics. The discovery of an 11th dimension that didn't just add another layer to reality, but rewrote the rules entirely. M theory, born from this revelation, didn't merely patch together the 5 competing string theories. It revealed they were all facets of something grander, like fingers on a hand we'd only glimpsed one at a time. At its core, this framework trades strings for something even more exotic, membranes or branes fluttering through an 11-dimensional expanse. Picture our universe not as a solitary stage, but as one sheet in a vast cosmic stack, each vibrating with its own laws, its own history, its own version of reality. This leap to 11 dimensions isn't arbitrary. It's the key to unlocking puzzles that 10 dimensions couldn't solve. Take black holes, those enigmatic voids where gravity crushes matter into oblivion. In M theory, they're mind-bending entropy. The chaos hidden beneath their event horizons finally makes sense when you account for branes stretching across higher dimensions. Imagine a black hole not as a pit, but as a tangled knot of membranes, its heat and disorder arising from how these surfaces twist and intersect in realms beyond our perception. It's as if we've been studying smoke while ignoring the fire, and the 11th dimension is the flame itself. Even more radical is the holographic principle, the idea that our three-dimensional universe might be a projection from a two-dimensional boundary, like a movie encoded on a DVD's flat surface. In M theory, this isn't just metaphor, it's geometry. The 11th dimension could be the canvas where this cosmic hologram is painted, with brains acting as projectors casting shadows we mistake for solid reality. Think of a streetlight's glow on a foggy night. The light itself is invisible, but its effects are everywhere. Higher dimensions might play the same role, unseen but shaping every law of physics, every particle collision, every flicker of starlight. What's astonishing is how these ideas bridge the microscopic and the cosmic. A brain collision in 11 dimensions might have sparked our Big Bang, while quantum entanglement could be particles whispering to each other across hidden folds in spacetime. And though we can't yet step outside our three-dimensional cage to witness these wonders directly, the math leaves trails to follow, like gravitational waves carrying echoes of brains colliding, or particle accelerators hunting for energy vanishing into the bulk. The universe, it seems, has been leaving breadcrumbs all along. We're just learning how to read them. Beyond the 10th dimension, the landscape of string theory stretches into uncharted territory, dimensions 21 through 30, where the very rules of reality begin to blur. These aren't just extra directions in space, they're the playgrounds of radical ideas, where particles might wear invisible disguises and universes could nest like Russian dolls. Some models suggest these dimensions harbor shadow matter, particles identical to ours but utterly oblivious to the forces that bind our world. Picture a ghostly twin of every electron and quark, drifting through walls, passing through planets, its existence betrayed only by the faintest gravitational tug. Entire galaxies could be built from this phantom stuff, invisible yet woven into the fabric of everything. Other theories go even further, proposing that these dimensions aren't physical at all but abstract scaffolds, mathematical bookkeeping devices that keep the equations coherent. Think of them as the hidden gears in a cosmic clock, unseen yet essential for the machinery to tick. Without them, string theory's delicate balance would collapse, like a house of cards missing half its pieces. But here's the twist. Even if these dimensions lack physical form, their influence could be profound. The way numbers arrange themselves in higher dimensional math might determine why our universe has exactly 3 spatial dimensions we can perceive, while the others remain locked away. Then there's the wildest possibility, that dimensions 21 through 30 are the backstage of the multiverse. Imagine a vast cosmic library where each book is a universe with its own laws, its own constants, its own version of time. Our reality might just be one volume on a shelf stretching into infinity, with higher dimensions acting as the glue between them. Collisions between these universes could explain cosmic mysteries like dark energy or the uneven glow of the Big Bang's afterglow. It's a dizzying thought. Every time a particle behaves unpredictably in a quantum experiment, it might be feeling the whisper of a neighboring universe brushing against ours through these hidden dimensions. The debate over whether these dimensions are real or just mathematical tools cuts to the heart of theoretical physics. Some argue that if a dimension can't be observed, even in principle, it's no more real than a character in a story. Others counter that mathematics has a habit of revealing truths long before experiments catch up. Black holes were once dismissed as mathematical quirks, after all. What's thrilling is that we're finally asking the right questions, even if the answers lie beyond our current reach. Whether these dimensions are shadows, scaffolds, or secret passageways to other worlds, they remind us that the universe is far stranger and far richer than we ever dared to dream. Imagine walking past a skyscraper every day without ever realizing it's hollow, its vast interior hidden behind an ordinary facade. That's the essence of the cosmic sleight of hand that could explain why 30 dimensions coexist with our familiar 3, yet remain entirely invisible. The idea isn't new. Back in 1919, a mathematician proposed something radical. If equations were rewritten to include a fifth dimension, an extra term appeared that perfectly described electromagnetism. It was as if the universe had been whispering its secrets in a language we'd only just begun to decipher. His colleague later refined the idea, suggesting this fifth dimension wasn't missing. It was just curled up smaller than an atom, like a garden hose viewed from a mile away. But how does this apply to string theory's dizzying 30 dimensions? Think of space as a loaf of bread, where each slice represents our three-dimensional world. Now imagine that between these slices lie countless others, compressed into shapes so intricate they resemble fractal origami. These are manifolds, six-dimensional geometries that might determine everything from the mass of an electron to the strength of gravity. Picture a single point in your living room. At that spot, according to, there isn't just emptiness. There's an entire folded universe, a labyrinth of dimensions smaller than a quark, vibrating with the energy of unseen strings. The real magic lies in how these hidden folds shape the laws of physics. Just as the grooves in a vinyl record transform into music when touched by a needle, dimensions play the particles we observe. For example, the way a string vibrates through these folds could explain why electrons carry negative charge while protons are positive. The geometry itself becomes the rulebook for reality. Even more astonishing, variations in these shapes might spawn entirely different universes. A slight twist in the manifold could swap electrons for muons, turn gravity repulsive, or erase atoms altogether. Our universe's delicate balance, the precise tuning that allows stars and planets to exist, might just be one possible arrangement in a vast landscape of hidden geometries. Yet isn't without its mysteries. Why do dimensions curl up at all? One compelling answer comes from the early universe, moments after the Big Bang. As spacetime expanded, some dimensions might have stretched while others remained tightly wound, like strands of taffy pulled in opposite directions. Or perhaps gravity itself played a role, acting as a cosmic loom that wove certain dimensions into the background. Whatever the mechanism, the implications are staggering. Dark matter could be ordinary particles trapped in these folds, while quantum entanglement might be particles communicating through shortcuts in higher dimensional space. The most poetic part turns every corner of the cosmos into a Russian nesting doll of hidden realities. The screen you're staring at, the air you're breathing, all might be threaded with dimensions too small to see but too fundamental to ignore. It's a reminder that the universe loves to hide its greatest wonders in plain sight, waiting for those bold enough to look beyond the obvious. Picture waking up one day to discover your entire life has been unfolding on the surface of a soap bubble, floating alongside countless others in a vast cosmic foam. This isn't a hallucination, it's the hypothesis, a radical reimagining of reality where our three-dimensional universe is just one membrane, or brane, adrift in a higher dimensional expanse. Unlike the curled-up dimensions of string theory, these extra dimensions could be infinite, stretching endlessly beyond our perception. The catch: we're trapped on our brain like ants on a leaf, unable to step off or see beyond its edges. What makes this idea so compelling is how neatly it solves some of physics' greatest puzzles. Take gravity's puzzling weakness compared to other forces. If electromagnetism and the nuclear forces are like glue-sticking particles to our brain, gravity might be the only force free to seep into the bulk, the higher dimensional space around us. Imagine water soaking through a sponge. What feels feeble in our world could be gravity's strength diluted across dimensions we can't access. This leakage could explain why gravity is 10 trillion times weaker than electromagnetism. It's not inherently weak, it's just spread thin. Then there's dark energy, the mysterious force accelerating the universe's expansion. offer a startling possibility. What if it's not a force at all, but the gentle tug of a neighboring brane drifting through the bulk? Picture two magnets repelling each other without touching. Our universe might be feeling the push of another membrane hovering nanometers away in a higher dimension, its presence detectable only through the cosmos, relentless expansion. But why haven't we glimpsed these extra dimensions if they're all around us? The answer lies in their geometry. Think of a train racing along parallel tracks. From inside a carriage, you'd never notice the other trains unless they crossed your path. Similarly, parallel branes could exist mere lengths away, far closer than an atom's nucleus, yet remain invisible because everything we see and touch is stuck to our membrane. Even light, confined to our brain, can't escape to illuminate what lies beyond. The most mind-bending implication: collisions between branes might not be rare catastrophes but cosmic resets. Some theorists suggest our Big Bang was the aftermath of two branes smashing together, recycling a previous universe's energy into our own. If true, the echoes of that collision could still ripple through the cosmos, etched into the microwave background radiation like scars on spacetime. Future telescopes might one day spot these fingerprints, revealing we're not just inhabitants of a brane, but survivors of a higher dimensional crash. For now, remain a tantalizing what if, but the math refuses to let them go. From gravity's quirks to dark energy's enigma, the answers we seek might not lie in our universe at all, but in the unseen dimensions brushing against it, whispering secrets we're only beginning to decode. Every note in a symphony arises from the same instrument, just played differently. In string theory, the universe works the same way. Quarks, electrons, photons. They're not fundamentally different objects, but variations of the same tiny, vibrating string. Picture a single violin string producing an entire orchestra's worth of sound by resonating at different frequencies. Now shrink that string down to a billionth of an atom's size, and you've got the basic idea. The cosmos as a grand composition, with every particle a unique note in the score. What determines these notes? The hidden dimensions curled up inside shapes. Think of these six-dimensional geometries as the universe's tuning pegs. Just as tightening a guitar string changes its pitch, the way strings stretch and twist through these folded dimensions alters their vibrations, and thus the particles they become. An electron isn't a dot, but a string humming at one particular frequency. A quark. The same string vibrating at a higher harmonic, like playing the second harmonic on a violin by lightly touching the string's midpoint. Even the boson, the particle that gives others mass, might just be a deeper resonance, a bass note thrumming through the fabric of spacetime. The magic lies in the harmonics. Pluck a string, and it doesn't just produce one pure tone, it generates overtones, subtle layers of sound that give each instrument its richness. Strings in higher dimensions do something eerily similar. Their overtones aren't music to our ears, but matter to our world. A slight shift in the geometry of those hidden dimensions could turn an electron into a muon or make gravity 10 times stronger. It's as if the universe composed its laws by tweaking the shape of an invisible instrument, fine-tuning reality through vibrations we're only beginning to understand. Here, where it gets even wilder. These vibrations don't just create particles, they might explain why particles have properties like charge and spin. Imagine a jump rope whirling in a spiral. The way it twists defines its motion. Similarly, a string vibrating through a manifold's folds could twist in ways that give rise to an electron's negative charge or a quark's fractional spin. The dimensions themselves become the rulebook, their geometry dictating the rules of the game. Yet the symphony isn't set in stone. Early in the universe's history, those hidden dimensions might have vibrated chaotically, shifting until they settled into stable configurations. Some physicists speculate this could explain why we have exactly 3 generations of particles, electrons, muons, and taus, each heavier than the last. Like a chord resolving into harmony, the dimensions found arrangements that allowed matter as we know it to exist. The beauty of this idea isn't just its elegance, but its testability. If strings vibrate at specific frequencies, particle colliders might one day spot the missing notes particles predicted by the math but not yet observed. Or gravitational wave detectors could catch subtle distortions in spacetime's fabric, echoes of strings oscillating in dimensions beyond our sight. Every experiment probing the subatomic world is, in a way, listening for the universe's hidden melody. And if we're right, the music has been playing all along. We just needed to learn how to hear it. Supersymmetry isn't just another layer to the universe. It's a cosmic mirror, reflecting every particle we know into a hidden twin we've never seen. Picture the subatomic world as a grand ballroom where fermions, the particles that make up matter, dance in sharp, precise steps, while bosons, the force carriers, swirl in smooth, flowing motions. Supersymmetry, or SUSY, suggests there's a deeper harmony to this dance. For every fermion, there's a bosonic superpartner and vice versa. Electrons would have, quarks would have squarks, and even the photon, the particle of light, would have a shadowy counterpart called the photino. This symmetry isn't just poetic, it's a mathematical necessity solving problems that have haunted physicists for decades. Take the infamous hierarchy problem. The boson's mass should be driven to impossibly high energies by quantum corrections, like a constantly battered by waves. But SUSY stabilizes this, with superpartners canceling out those corrections like perfect dance partners counterbalancing each other's moves. Without supersymmetry, the math collapses into absurdity, suggesting this should weigh a quadrillion times more than it does. Yet here's the catch. If these superpartners exist, why haven't we spotted them? The Large Hadron Collider has scoured energy levels where they should appear, finding nothing but empty space. This absence doesn't spell the end of SUSY, it might just mean we're looking in the wrong dimensions. Superpartners could be hiding in higher dimensional folds, their masses stabilized by geometries too small for our colliders to probe. Imagine searching for a whisper in a hurricane. If the extra dimensions are beyond our current reach, these particles might be just out of earshot. Some theories even suggest superpartners could be folded into shapes, their signatures blurred like a fingerprint smudged on glass. The implications stretch far beyond particle physics. SUSY's superpartner, often is a prime candidate for dark matter, a particle that doesn't emit light but could make up 27% of the universe. Picture a cosmic game of hide-and-seek, where these invisible particles pass through you right now, their gravity silently sculpting galaxies. If SUSY is real, dark matter might not be exotic at all, just the shadow of a symmetry we're only beginning to trace. Critics argue SUSY's elegance doesn't guarantee its truth, and they're right. Nature isn't obligated to satisfy our aesthetic preferences, but the math's persistence is telling. From stabilizing string theory to explaining dark matter, supersymmetry weaves through physics' greatest puzzles like a golden thread. Whether it's confirmed or not, SUSY has already reshaped how we see the universe, not as a collection of disparate parts, but as a tapestry of hidden connections, waiting for the right moment to reveal themselves. Black holes have long been the universe's ultimate enigmas, cosmic vacuum cleaners sucking in everything, even light. But what if they're not just destructive pits? What if they're tangled knots in the fabric of higher dimensional space, their very existence pointing to realms beyond our perception? String theory paints a startling picture. Black holes might be the closest thing we have to a backstage pass to the hidden dimensions shaping reality. Take their entropy, for instance. In classical physics, entropy measures disorder. Think of a shattered glass versus an intact one. But black holes defy this logic. Their entropy isn't tied to messy particles. It's encoded on their event horizons, the boundaries where gravity becomes inescapable. String theory cracks this code by suggesting the chaos isn't on the surface at all. It's in the way strings stretch across higher dimensions, weaving intricate patterns too small to see. Picture a tangled ball of yarn where every thread represents a string vibrating in a hidden dimension. The more complex the tangle, the higher the entropy. Suddenly, black holes aren't just chaotic, they're cosmic stones, their entropy whispering secrets about dimensions we can't yet touch. Then there's Hawking radiation, the faint glow predicted to leak from black holes as they evaporate. If extra dimensions exist, this radiation might carry their fingerprints, unusual energy signatures or particles that shouldn't exist in a three-dimensional world. Imagine baking a loaf of bread with a hidden ingredient. You might not see the spice, but its flavor gives it away. Similarly, Hawking radiation could be the flavor, hinting at higher dimensions, detectable in labs like the Large Hadron Collider if we know what to look for. The wildest possibility, microscopic black holes. In a four-dimensional world, these would evaporate instantly, but in higher dimensions, they could linger just long enough to leave traces. Some theories suggest cosmic rays striking Earth's atmosphere might briefly create these tiny portals, their decay patterns betraying the presence of unseen dimensions. It's like finding a footprint in the sand. You don't see the creature that made it, but the shape tells you it's unlike anything you've encountered. What makes black holes so compelling isn't just their mystery, but their potential as laboratories. They bend spacetime so severely that they might pry open cracks to higher dimensions, offering glimpses of physics beyond wildest dreams. Whether through their entropy, their radiation, or their microscopic cousins, these cosmic anomalies could be the key to unlocking string theory's boldest claims, and proving we're living in a universe far stranger than we ever imagined. What if everything you see around you, the screen in front of your eyes, the chair beneath you, even your own hands, is nothing more than an illusion, a holographic projection from a cosmic boundary we can't perceive? This isn't science fiction. It's the holographic principle, one of the most startling ideas to emerge from string theory's exploration of higher dimensions. The concept flips our understanding of reality on its head, suggesting that all the information in our three-dimensional universe might be encoded on a two-dimensional surface, like a movie stored on a DVD. The world we experience would then be the projection, the hologram playing out from that hidden code. The roots of this idea trace back to the study of black holes. In the 1970s, physicist Jacob discovered something bizarre. A black hole's entropy, a measure of its hidden chaos, doesn't depend on its volume but on the area of its event horizon. It's as if all the complexity inside a black hole is smeared across its surface, not packed into its depths. Decades later, string theorists took this further, proposing that the entire universe might work the same way. Their AD-SCFT correspondence became the stone for this radical notion, linking gravity in a higher dimensional space, anti-Sitter space, to a quantum field theory living on its lower dimensional boundary. Think of it like a shadow puppet show. The puppets themselves are flat, but their shadows cast on the wall appear three-dimensional, full of depth and movement. In the holographic universe, our 3D reality could be the shadow, the projection of quantum information dancing on a distant 2D surface. Even stranger, this isn't just a metaphor. The math suggests that every event in our world, from a supernova explosion to the firing of a neuron in your brain, corresponds to precise interactions on that boundary. Gravity, time, even the sensation of solidity might be emergent phenomena, illusions generated by the way information is processed at the edge of existence. But how could this possibly work? Consider a computer simulation. The world inside the screen feels real to its characters, but it's ultimately just code running on a processor. The holographic principle takes this a step further. The processor isn't a machine, it's the fabric of spacetime itself, with the universe's underlying information etched onto its outer shell. This would explain why quantum mechanics and gravity seem so incompatible. They're not fighting for dominance in our 3D world, but operating on different levels of the cosmic hologram. Quantum entanglement, where particles instantly influence each other across vast distances, might just be threads in the underlying code, shortcuts written into the 2D surface that appear as spooky action in our 3D projection. The implications are staggering. If the holographic principle is correct, then black holes aren't just cosmic vacuum cleaners. They're the universe's hard drives, storing information in ways we're only beginning to fathom. Dark energy, the mysterious force accelerating the expansion of the cosmos, might be a glitch in the projection, a sign that the hologram's resolution is stretching thin. Even time itself could be an illusion, a byproduct of how information is updated on the boundary, like frames in a film creating the illusion of motion. Skeptics argue that this is all just elegant math without experimental proof, and they're right for now. But the hunt for evidence is on. Gravitational wave detectors might one day catch subtle anomalies, patterns that don't fit equations but align with holographic predictions. Quantum computers could simulate tiny holographic universes, letting us test the principle in silicon before confirming it in nature. And if we're right, it would mean that every star, every planet, every one of us is a kind of cosmic mirage, a shimmering projection of something far simpler and far stranger than we ever dared to believe. If our universe is just one page in an infinite cosmic library, then extra dimensions might be the shelves holding countless other worlds, each with its own rules, its own history, its own version of reality. This is the multiverse hypothesis, where string theory's hidden dimensions don't just shape our universe but host an unimaginable plurality of others. Picture a frothing ocean where every bubble is a self-contained cosmos floating in a higher dimensional sea. Some might have gravity 10 times stronger than ours, making stars burn out in seconds. Others could lack electromagnetism entirely, their atoms drifting in darkness without light or chemistry. The most startling part. String theory's math doesn't just allow for this, it practically demands it. At the heart of this idea lies the landscape, a vast terrain of possible universes predicted by string theory's equations. Think of it as a cosmic game of chance, where every roll of the dice produces a new set of physical laws. The manifolds we've explored, those six-dimensional shapes curled into every point in space, might take on slightly different geometries in each universe, tweaking the vibrations of strings to create alternate physics. Some configurations could spawn worlds where protons decay instantly, rendering matter impossible. Others might generate universes drowning in dark energy, tearing themselves apart moments after birth. With an estimated 10 to the power of 500 possible vacuum states, the numbers defy comprehension. That's more potential universes than atoms in our observable cosmos. One compelling version of this multiverse comes from scenarios. Imagine our universe as a slice of bread in an infinite loaf, where other slices hover millimeters away in a higher dimension, close enough to feel their gravity but forever out of reach. These parallel branes could collide, triggering big bangs that birth new universes. Some theorists suggest our own cosmic dawn might have been the aftermath of such a collision, with the energy of two membranes smashing together, recycled into the galaxies and stars we see today. The echoes of that impact could still linger in the cosmic microwave background, subtle wrinkles waiting to be decoded by future telescopes. Then there's the quantum multiverse, where every decision spawns a new reality. In this view, higher dimensions aren't just physical spaces but branching timelines, each representing a different outcome of quantum events. A single electron's path could split the universe into two, one where it went left, another where it went right. Layer this with string theory's extra dimensions, and you get a fractal of possibilities. Worlds where dinosaurs never went extinct, where humans evolved gills, or where the laws of thermodynamics run backward. Critics argue this sounds less like science and more like metaphysics, and they're not entirely wrong. Testing these ideas is notoriously difficult but not impossible. If parallel branes exist, their gravity might subtly tug on our universe, leaving faint distortions in the large-scale structure of galaxies. Quantum experiments could uncover anomalies, particles behaving as if they're interacting with invisible copies of themselves across dimensions. Even the mysterious cold spot in the cosmic microwave background, a region eerily devoid of galaxies, has been proposed as a bruise from a long-ago collision with another universe. What's profound isn't just the scale of these ideas, but what they imply about our place in the cosmos. If the multiverse is real, then the fine-tuning of our universe, the precise constants that allow stars, planets, and life to exist, might not be a miracle but a statistical inevitability. With infinite rolls of the dice, some universes were bound to hit the jackpot. The question isn't just whether we're alone in our universe, but whether our universe is alone in the grand tapestry of dimensions, or just one thread in a weave too vast to fathom. Time slips through our fingers like sand, yet in string theory, it might not be the steady river we perceive, but something far stranger. Unlike the three spatial dimensions we move through daily, time has always stood apart, flowing in one direction, marking the arrow of entropy. But what if that's just an illusion? Some models in string theory suggest time isn't fundamental at all. Instead, it could emerge from the interplay of higher dimensions, like a melody arising from the vibrations of unseen strings. Picture a clock whose ticking isn't driven by gears but by the way strings stretch and twist through hidden geometries. Time, in this view, isn't a backdrop. It's a symphony played out across dimensions we can't see. Take closed curves, hypothetical paths where time loops back on itself. In general relativity, these curves are mathematically possible, but they require extreme conditions like the gravity near a spinning black hole. String theory adds a tantalizing twist. Extra dimensions might make these loops far more accessible. Imagine a hiker circling a mountain, returning to their starting point. Now replace the mountain with a higher dimensional shape and the hiker with a particle traveling through time. The right geometry could let a string vibrate its way into the past, not by breaking physics, but by threading through folds in spacetime too small for us to perceive. The implications are dizzying. If time is emergent, the Big Bang might not be the true beginning but a phase transition, a shift in how higher dimensions arrange themselves, like ice melting into water. Even our perception of cause and effect could be a shadow of deeper, timeless physics. Some theorists propose that what we call time is just a holographic projection, a narrative stitched together by quantum entanglement across dimensions. In this picture, the past, present, and future might all exist simultaneously, frozen in a block universe where change is an illusion born from our limited perspective. Skeptics argue that closed curves create paradoxes. What happens if you go back and prevent your own birth? But string theory offers a sly escape. Those extra dimensions could enforce quantum consistency, ensuring any time travel only plays out in self-consistent loops. Like a painter who can't erase their strokes but can layer over them, time travelers might find their actions woven into history seamlessly, their free will constrained by the geometry of reality itself. The wildest possibility, time might not even be universal. In scenarios, parallel universes could experience time at different rates or not at all. A second to us might be an eternity on a neighboring brane, with particles hopping between membranes appearing to vanish or age unpredictably. This could explain anomalies like quantum tunneling, where particles seemingly teleport through barriers. They might not be jumping, they're slipping through wrinkles in time's higher dimensional fabric. For now, these ideas remain in the realm of theory, but the math refuses to let them go. Whether time is fundamental or emergent, a river or a loop, one thing is clear. Our understanding of it is due for a revolution. And when that day comes, we might find that the past, present, and future aren't what we thought, just different notes in a cosmic song we're only beginning to hear. Quantum entanglement has long been physics' greatest magic trick, particles separated by light years instantly mirroring each other's states, as if space and time don't exist. Called it spooky action at a distance. But what if the spookiness isn't a flaw in reality but a clue? String theory offers a startling possibility. Entangled particles might not be communicating faster than light. They could be threading through hidden dimensions, passing signals along shortcuts our three-dimensional minds can't perceive. Think of it like ants crawling on a folded piece of paper. To the ants, two dots on opposite sides seem far apart until you fold the paper, bringing them into contact. Similarly, particles entangled at the quantum level might be inches apart in a higher dimension while appearing light years away in our familiar space. This isn't just poetic speculation. The math of string theory allows for these invisible bridges, where strings vibrating in extra dimensions create correlations that defy classical physics. The real breakthrough came when physicists realized entanglement's non-locality. The eerie linked behavior of particles could be a natural feature of a holographic universe. If our three-dimensional world is a projection from a two-dimensional boundary, as the holographic principle suggests, then entangled particles might be touching on that deeper layer, their connection mediated by information we can't see. Picture two puppets controlled by the same strings. Their movements seem coordinated, not because they're signaling each other, but because they're tied to the same hidden framework. Even more radical is the idea that entanglement could be evidence of wormholes, tiny tunnels through higher dimensional space. And proposed these bridges, now called bridges, as theoretical curiosities, but string theory suggests they might be everywhere, woven into the quantum foam. When particles entangle, a microscopic wormhole could form between them, threading through a fifth or sixth dimension. It's as if every quantum handshake doesn't just link particles, it stitches spacetime itself into new geometries. Critics argue this swaps one mystery for another, and they're not wrong, but the elegance is undeniable. Entanglement's randomness in our dimensions might be strict causality in higher ones, like watching shadows on a wall and missing the objects casting them. Future experiments could test this by probing entanglement's limits, searching for subtle deviations that hint at extra-dimensional leakage. Until then, the universe keeps its secrets close, whispering them through particles that dance in lockstep across the void, as if sharing a secret we're only beginning to decipher. 95% of the universe is missing. Not misplaced, just invisible, undetectable by any telescope or instrument we've built. Dark matter and dark energy, the twin shadows looming over modern cosmology, defy every conventional explanation. But what if we've been searching in the wrong dimensions? String theory paints a provocative picture. These cosmic ghosts might not be hiding in our three-dimensional world at all, but lurking in the folds of higher dimensional space, their influence spilling into our reality like whispers through a wall. Take dark matter first. We know it's there. Galaxies rotate too fast for the visible matter holding them together, like a merry-go-round spinning so violently its riders should fly off. Yet something unseen grips the stars, keeping them in place. Traditional candidates like WIMPs, weakly interacting massive particles, have eluded detection for decades. But string theory offers an alternative. Dark matter could be ordinary particles tethered to higher dimensions, their gravity leaking into our world while they remain forever out of reach. Picture a room filled with balloons. From outside, you see only their shadows, flat, distorted versions of the real objects. Dark matter might be like those balloons, existing fully in extra dimensions while casting gravitational shadows we mistake for particles. The numbers align eerily well. If dark matter particles move freely through higher dimensional space, their apparent weakness in our world isn't intrinsic, it's diluted like a scent diffusing through a vast house. Some models even suggest dark matter could be strings vibrating exclusively in hidden dimensions, their energy manifesting only as gravity in our brain. Collider experiments might one day spot anomalies, missing energy or skewed particle tracks that betray these higher dimensional travelers. Until then, their presence is written in the way galaxies cluster, the way light bends around empty space, the way the cosmos refuses to behave without them. Dark energy is an even deeper enigma. Unlike dark matter, which clumps around galaxies, dark energy permeates every inch of space, pushing the universe apart at an accelerating rate. The simplest explanation is a cosmological constant, a uniform energy woven into spacetime itself. But string theory whispers a wilder possibility. Dark energy could be the tension of our stretching in a higher dimensional bulk. Imagine living on the surface of a balloon as it inflates. To you, space isn't just expanding. Every point is moving away from every other, not because things are flying apart, but because the fabric beneath you is stretching. Now replace the balloon with our three-dimensional brain and the air with dark energy, and you've got a compelling metaphor for cosmic acceleration. The math gets even more intriguing when you consider brain collisions. Some theories suggest dark energy's strength isn't constant, but varies as our brain drifts closer to or farther from neighboring membranes in the bulk. Like magnets repelling at a distance, these unseen interactions could be driving the universe's expansion, with fluctuations in dark energy corresponding to shifts in higher dimensional geometry. If true, the fate of the cosmos, whether it tears apart, collapses, or stabilizes, might hinge on dimensions we'll never see directly. What ties these ideas together is a radical rethinking of empty space. The vacuum isn't nothing. It's a seething quantum foam where strings and brains twist through hidden dimensions. Dark matter could be the gravity of strings vibrating in a parallel fold, while dark energy reflects the elastic tension of spacetime itself. The answers to cosmology's greatest mysteries might not require new particles or forces, just a willingness to accept that reality is far bigger and far stranger than the slice we call home. For now, these ideas linger at the edge of testability. But as gravitational wave detectors grow more sensitive and particle colliders probe higher energies, we might catch glimpses of the unseen dimensions shaping our universe. Until then, the darkness isn't just a void, it's a canvas, waiting for physics to illuminate the hidden brushstrokes of a multidimensional masterpiece. Hidden within every point of our three-dimensional world could lie a labyrinth so complex, it makes MC's drawings look like child's play. These are manifolds, six-dimensional shapes so finely twisted and folded, they could fit inside a speck of dust, yet dictate everything from the mass of an electron to the fate of galaxies. To grasp their strangeness, picture a world where directions don't stop at up-down or left-right, but spiral into 6 new axes, each curling back on itself in patterns no human eye could ever trace. This isn't abstract art, it's the hidden geometry that might underpin reality itself. What makes these shapes so special? First, they're the ultimate problem solvers. String theory's equations demand extra dimensions, but they can't sprawl endlessly like our familiar space. They need to curl up tightly, like a frenetic origami masterpiece. Manifolds achieve this while preserving supersymmetry, the delicate balance between matter and force particles. Think of them as cosmic tuning forks. Their specific resonances determine how strings vibrate, which in turn defines whether those vibrations become quarks, photons, or bosons. A single kink in their geometry could rewrite the periodic table or render gravity repulsive. The math behind these shapes is breathtaking. Named after mathematicians and Sheeing, these manifolds aren't just any six-dimensional objects. They're solutions to a set of equations so restrictive, discovering them felt like finding a needle in a universe-sized haystack. To qualify as a shape must satisfy three brutal conditions. It must be flat, meaning no intrinsic curvature, like a sheet of paper rolled into a cylinder, possess a special kind of symmetry called SU3, and admit something called a metric. The result, a structure so finely balanced it's been likened to a diamond suspended in a spider web, each facet perfectly aligned, each tension exquisitely calibrated. But here, where it gets wild, these manifolds aren't unique. There are millions of possible configurations, each a potential blueprint for a different universe. Some resemble intricate knots, others mimic multi-chambered beehives. Their topology, the way their holes and handles are arranged, could determine why our universe has three generations of particles, electrons, muons, taus, or why gravity is so weak compared to electromagnetism. Imagine a cosmic game of where strings fall through these multidimensional mazes, bouncing off curves and tunnels to emerge as distinct particles. The maze's design is the of physics. The real magic lies in how these shapes solve string theory's greatest headaches. Without them, extra dimensions would destabilize the theory, causing particles to vanish or forces to go haywire. Manifolds act like cosmic shock absorbers, chaos into order. For example, their geometry naturally explains chirality, the fact that particles like neutrinos spin only left-handed in our universe. In higher dimensions, strings winding around us loops pick up handedness like a vine twisting around a trellis, translating into the spin states we observe. Yet for all their elegance, these manifolds remain frustratingly elusive. We can't probe them directly, but their fingerprints are everywhere. Particle colliders might one day spot anomalies, missing energy or skewed collision patterns that betray strings vibrating in hidden folds. Gravitational wave detectors could catch echoes of geometries warping spacetime. Until then, they stand as both masterpiece and mystery, reminding us that the universe's deepest truths may be written in a language of shapes we're only beginning to sketch. For all its mathematical elegance, string theory remains one of the most polarizing ideas in modern physics. A breathtaking vision of hidden dimensions that some hail as the theory of everything, while others dismiss as an untestable fantasy. The debate isn't just academic. It cuts to the very definition of what makes a scientific theory valid. Critics like Nobel laureate Sheldon have famously compared string theory to medieval theology, intricate, beautiful, but ultimately disconnected from observable reality. Their core complaint: after half a century of research, string theory still hasn't produced a single definitive prediction that experiments can confirm or refute. In a field where progress is measured by particle collisions and precision measurements, that's a glaring problem. Take the multiverse hypothesis. If string theory's landscape allows for 10 to the power of 500 possible universes, each with different physical laws, how do we prove ours isn't just a statistical fluke? Detractors argue this isn't science, it's speculation disguised as profundity. Even the theory's proposed tests, like microscopic black holes at the Large Hadron Collider, have yielded nothing but silence. To skeptics, this absence of evidence isn't just disappointing, it's damning. As physicist Peter bluntly put it in his book, Not Even Wrong, string theory risks becoming a self-referential game, divorced from the messy business of experimental validation. Yet defenders counter that dismissing string theory for its current ignores history. General relativity was once deemed abstract and impractical until eclipses confirmed light bending around the sun. The boson took 50 years to detect. The math, they argue, is too compelling to ignore, especially when it effortlessly unites quantum mechanics and gravity, two frameworks otherwise at war. String theory's equations don't just accommodate extra dimensions, they require them, with a consistency that feels like uncovering a hidden rulebook of reality. For proponents like, this mathematical harmony suggests we're glimpsing something profound, even if the technology to prove it lags behind. The standoff reveals a deeper tension in physics, between empiricists who demand testable results and theorists who chase elegance. String theory's allure isn't just its potential to explain the cosmos, but its sheer beauty, a quality that, while subjective, has guided breakthroughs before. Sequation predicting antimatter emerged from aesthetic symmetry, not experimental data. The question is whether string theory is true in some absolute sense, but whether its mathematical fertility justifies the gamble. As we push the boundaries of energy and observation, the answer may yet materialize, not as a eureka moment, but as a slow unraveling of the universe's deepest layers. Until then, the theory remains suspended between inspiration and frustration, a reminder that science's greatest ideas often outpace our tools to confirm them. The hunt for extra dimensions isn't confined to chalkboards and equations. It's playing out in the world's most powerful laboratories, where scientists sift through subatomic debris and cosmic static for whispers of the unseen. At the Large Hadron Collider, protons collide at nearly the speed of light, recreating conditions a fraction of a second after the Big Bang. While the LHC hasn't yet spotted strings or manifolds, it's searching for something just as telling: energy that vanishes without a trace. In a three-dimensional world, energy is always accounted for, but if particles occasionally slip into higher dimensions, carrying away momentum, these missing energy events could be their calling cards. It's like hearing footsteps in an empty hallway. You might not see the source, but the evidence is undeniable. Gravitational wave detectors offer another tantalizing avenue. When black holes merge, the resulting ripples in spacetime carry imprints of their origins. Some models predict that if extra dimensions exist, these waves would bear subtle distortions, extra frequencies or damping effects caused by gravity leaking into hidden realms. Imagine dropping a pebble into a pond and noticing the ripples don't spread evenly. That irregularity could hint at unseen depths beneath the surface. In 2017, the LIGO Observatory detected gravitational waves from a neutron star collision. While no anomalies were found, future upgrades could spot deviations too faint for current instruments, potentially uncovering gravity's secret ties to higher dimensions. Even the cosmic microwave background, the afterglow of the Big Bang, holds clues. Tiny temperature variations in this ancient light might encode patterns from the universe's birth, including echoes of brane collisions or the imprint of dimensions. Some theorists argue that certain anomalies, like the infamous cold spot, could be bruises from a long-ago encounter with another universe in the bulk. It's forensic cosmology, piecing together a crime scene 14 billion years old, where the fingerprints might be written in geometry rather than dust. Then there's the search for miniature black holes. In a universe with extra dimensions, gravity's strength could increase dramatically at microscopic scales, making tiny black holes far easier to produce than in classical physics. The LHC hasn't found them yet, but their absence isn't proof against higher dimensions, just a hint that the energy threshold might be higher than we've probed. Future colliders, like the proposed Future Circular Collider, could reach energies where these quantum black holes flicker into existence, evaporating instantly but leaving telltale jets of particles in their wake. The most intriguing hints, though, might come from everyday particles behaving oddly. Muons, heavier cousins of electrons, wobble slightly more than predicted when placed in magnetic fields. This anomaly, measured at and Brookhaven, could be a sign of virtual particles popping in and out of higher dimensions, subtly altering the muon's properties. Similarly, the graviton, a hypothetical particle representing gravity's higher dimensional vibrations, might manifest as missing energy or unexpected resonances in particle decays. Skeptics caution that these anomalies could have mundane explanations, and they're right to demand rigor. But the allure of extra dimensions lies in their ability to tie up so many loose ends, gravity's weakness, quantum entanglement, even dark matter, with a single elegant framework. Whether the evidence arrives in a thunderclap or a whisper, the search itself is reshaping how we see the cosmos. Every null result narrows the possibilities. Every anomaly, however faint, keeps the dream alive. And if history is any guide, the universe's greatest secrets often reveal themselves to those patient enough to listen for the unexpected. Why does our universe appear tailor-made for life, with exactly 3 spacious dimensions where planets orbit stars and chemistry weaves complexity? The answer might lie in a simple but profound idea. We couldn't ask the question if it weren't true. This is the anthropic principle, the observation that the universe's laws must allow for conscious observers, because here we are asking why. If extra dimensions exist but are curled up impossibly tiny, or if gravity had leaked too much into the bulk, stars might never have ignited, atoms might never have bonded, and life as we know it would be impossible. The fine-tuning isn't luck, it's survival bias on a cosmic scale. But this raises a deeper question. Is our 3-dimensional reality the only possible configuration, or just one of countless failed experiments in a multiverse where most universes flicker out without witnesses? Imagine a vast cosmic casino where every roll of the dice spawns a new universe with random dimensions, physical constants, and laws. Most are stillborn, 11 sprawling dimensions where gravity crushes atoms instantly, or 2 flat dimensions too simple for intricate chemistry. A rare few, like ours, hit the jackpot. 3 roomy dimensions for stable orbits, plus tiny, hidden ones to shape quantum forces. We don't live in a special universe. We live in the only kind where beings like us could exist to call it special. Critics argue this smacks of surrender, replacing divine design with infinite dice rolls. But the math lends eerie support. String theory's landscape of possible shapes suggests an almost unfathomable variety, 10 to the 500th power or more, of potential universes, each with different physics. If even a vanishing fraction permit life, statistically, some observers would find themselves in hospitable corners. The alternative, that our universe is the lone, inexplicable miracle, feels equally staggering. The anthropic principle doesn't just explain dimensions, it reshapes how we see existence. Dark energy's precise weakness, the neutron's perfect balance, even the boson's mass, all might not be laws but local bylaws, quirks of our particular cosmic neighborhood. Future tests could tilt the scales. If colliders find particles behaving in ways only explicable by multiverse dynamics, or if telescope data reveals anomalies suggesting past brane collisions, the principle shifts from philosophy to physics. Until then, it stands as both humbling and exhilarating, a reminder that the universe might not be made for us, but we're made by it, in the sliver of reality where questions can be asked at all. For decades, string theorists wrestled with equations so complex they human intuition, until an unlikely ally arrived: artificial intelligence. Picture a mathematician staring at a manifold, its 6-dimensional folds twisting in ways no pen and paper calculation could fully capture. Now imagine an AI parsing those same shapes in seconds, spotting patterns invisible to the human eye. This isn't science fiction. Machine learning has begun mapping the labyrinthine geometries of string theory's hidden dimensions, turning what once took years into work completed over coffee breaks. The implications are staggering. We're no longer just imagining higher dimensions, we're training algorithms to navigate them. The breakthrough came when physicists realized AI could tackle string theory's most daunting hurdle, the vacuum problem. With an estimated 10 to the 500th power possible configurations for manifolds, finding the one matching our universe seemed like searching for a single atom in the observable cosmos. But neural networks trained on vast datasets of geometric configurations started predicting stable vacuum states, the mathematical ground rules for viable universes with uncanny accuracy. It's as if we've handed a master key to the cosmoses, letting machines test billions of dimensional blueprints while we watch for the one that fits. What makes this partnership revolutionary isn't just speed but perspective. Humans think in linear equations. AIs explore solution spaces like cosmic cartographers, charting territories no textbook could describe. Take MIT's work using generative adversarial networks, the same technology behind deepfake videos, to create never-before-seen shapes. These weren't random designs. They satisfied string theory's brutal mathematical constraints, suggesting geometries theorists had missed. Imagine an artist painting landscapes in 11 dimensions, each stroke governed by quantum consistency. That's the level of creativity AI brings to the table. The synergy goes deeper. String theory's equations often hit walls where traditional computation grinds to a halt. But machine learning thrives in ambiguity, finding approximate solutions that hint at deeper truths. When researchers fed an AI partial data on string dualities, mysterious equivalences between seemingly different theories, it reconstructed full relationships, uncovering shortcuts humans had overlooked. Like a translator decoding a lost language, the algorithm found coherence in what looked like chaos. Critics argue this risks replacing insight with brute force calculation, but the opposite may be true. AI doesn't diminish human creativity, it amplifies it. By handling the grunt work of testing millions of configurations, machines free theorists to ask bolder questions. Could certain shapes predict undiscovered particles? Might neural networks spot higher dimensional signatures in quantum noise? The tools are now in place to explore these frontiers in ways we've only dreamed of. The most tantalizing possibility: AI might uncover patterns pointing to experimental tests. If machine learning identifies a class of vacuum states that consistently produce 3 generations of particles, electrons, muons, taus, it could guide collider experiments toward specific energy signatures. Or if simulations reveal higher dimensional gravity leaking in predictable ways, telescopes could hunt for those fingerprints in cosmic structures. We're not just solving equations anymore. We're building bridges between abstract math and observable reality. This isn't the end of theoretical physics, it's a rebirth. Just as telescopes extended our vision beyond the visible spectrum, AI extends our intuition beyond 3 dimensions. The strings vibrating through hidden folds may still elude direct detection, but their echoes are now audible in the hum of supercomputers and the synaptic fires of neural networks. And somewhere in that digital symphony, the universe's deepest secrets might finally be coming into tune. String theory's wildest ideas didn't just revolutionize physics, they hijacked Hollywood's imagination. When Christopher needed a scientifically plausible way to bend time in Interstellar, he turned to Kip's work on higher dimensional gravity, visualizing the 5th dimension as where past and future collide like pages in a book. The result: a black hole's accretion disk wasn't just eye candy. It was a mathematically accurate rendering of spacetime warped by hidden dimensions, rendered so precisely it spawned new astrophysics papers. This is the cultural alchemy of string theory, abstract equations transformed into narrative gold, giving audiences visceral glimpses of realities beyond human perception. Marvel's Multiverse takes the concept even further, weaving string theories into blockbuster mythology. When Doctor Strange peers into alternate timelines or the Avengers battle variants across realities, they're riffing on theories like the string landscape, where every possible universe exists in a higher dimensional bulk. The Spider-Verse films, with their glitching characters and colliding dimensions, even borrow from quantum entanglement's spookiness, suggesting particles or people might communicate across membranes. It's not just storytelling, it's a stealthy education. By dressing up manifolds as quantum tunnels or portraying dark matter as a villain's power source, these stories make the esoteric tangible. A teenager leaving the theater might not grasp supersymmetry, but they'll remember the eerie beauty of parallel worlds brushing against our own. Video games have joined the fray too. No Man's Sky uses procedural generation to create a near-infinite universe, mirroring string theory's multiverse while letting players literally navigate higher-dimensional portals. Control's Oldest House warps architecture like a twisted space, where rooms reconfigure in impossible ways. These aren't just Easter eggs for physics nerds, they're empathy machines, letting players feel the disorientation of extra dimensions rather than just hearing about them. The irony is delicious. A theory once mocked as not even wrong now fuels narratives seen by billions. Whether it's Stranger Things, Upside Down, or Everything Everywhere All at Once's cosmic bagels, pop culture has become string theory's loudest megaphone. And perhaps that's the point. When equations fail to convince, a well-told story can spark the curiosity that leads to the next breakthrough. After all, every scientist was once a kid staring at the stars, or a movie screen wondering what else might be out there. If higher dimensions shape every particle, force, and law in our universe, what does that say about us, the minds observing it all? The question isn't just scientific, it's existential. Imagine living inside a painting, convinced the canvas is all there is, only to discover the artist's hand hovering beyond the frame. String theory's hidden dimensions suggest reality might work the same way. Our sense of free will, even our very consciousness, could be shadows cast by interactions in realms we can't perceive. Consider how we experience choice. You decide to lift your hand and it obeys, a clear act of will. But if every thought arises from particles obeying quantum laws, and those laws are dictated by strings vibrating in higher dimensions, where does you end and the geometry of reality begin? Philosophers call this the illusion of libertarian free will, the haunting possibility that our decisions are as predetermined as a ball rolling down a hill, just along slopes too complex for us to see. Yet there's a twist. If consciousness emerges from quantum processes, like the controversial OR theory suggests, those processes might be entangled with higher dimensional strings, making our minds participants in a cosmic feedback loop. Your choice to lift your hand could be both determined and free, like a river's path shaped by gravity yet still carving its own unique course. This taps into an even deeper mystery, the hard problem of consciousness. Why does any of this feel like something? If the brain is just particles interacting, why isn't it all happening in the dark? Some theorists speculate that qualia, the raw feel of experience, might be a higher dimensional phenomenon, akin to how a 2D shadow can't capture the depth of a 3D object. Your sensation of blue or the sting of grief could be fragments of a richer reality, filtered through our limited perceptual machinery. It's as if we're flatlanders trying to describe a symphony using only a single note. Then there's the eerie possibility of shared consciousness. If entangled particles communicate instantaneously across space, could minds entangled through higher dimensions do the same? Near-death experiences, or even collective creativity, might not be glitches but glimpses, like fish briefly breaching the surface of a pond, catching sight of a world beyond their own. The universe's hidden folds could be the medium connecting us in ways that defy classical physics, turning individuality into an illusion as fragile as a soap bubble. Skeptics argue this veers into mysticism, and they're not wrong to demand rigor. But the math nudges us toward humility. If string theory's extra dimensions are real, then reality isn't just stranger than we imagine, it's stranger than we can imagine. Our laws of logic, even our intuition about cause and effect, might be local bylaws in a single cosmic neighborhood. The true nature of existence could be as incomprehensible to us as a smartphone is to an ant. Yet here's the paradox: we're the universe observing itself. Those hidden dimensions, if they exist, gave rise to the very minds now trying to unravel them. In that sense, consciousness isn't just a passenger in this grand dimensional play, it's the universe's way of understanding its own script. And whether that script is predetermined or fluid, singular or infinite, one thing is certain. The act of asking the question changes the answer. Every thought, every experiment, every moment of wonder is another vibration in the strings, echoing through dimensions we're only beginning to sense. Explaining 30-dimensional math to students sounds like teaching a goldfish to visualize a hurricane. Yet educators are cracking this puzzle with tools that turn abstract nightmares into playgrounds of discovery. Take virtual reality, where a headset can transform a manifold 6-dimensional folds into an immersive landscape. Students don't just see these shapes, they navigate them, hands brushing against contours as if exploring a cave system. Apps like Dimensions let users rotate higher dimensional objects in real time, watching how a 4D cube casts shifting shadows in 3D space. These aren't gimmicks, they're cognitive bridges, leveraging our brain's knack for spatial reasoning to grasp the ungraspable. Analogies do similar heavy lifting. A classic, the ant on a rope metaphor. For a 2D ant crawling along a thin wire, the wire seems like a line until it's viewed under a microscope, revealing a cylindrical surface. That aha moment, realizing extra dimensions could be curled up like the wire's circumference, unlocks the core idea of. For younger learners, string art offers a tactile demo. Threads stretched across a board trace out complex curves, mirroring how strings vibrate through hidden dimensions to create particles. Even snack time becomes a lesson. Slicing a bagel at different angles produces interlocking rings, a delicious intro to how higher dimensional cuts could reveal bizarre topologies. But the real game changer is interactive simulation. Platforms like Shape by Google let users manipulate manifolds on a tablet, pinching and zooming to see how altering a dimension's radius changes particle properties. Imagine tweaking a virtual knob and watching an electron's mass update in real time, linking abstract math to tangible physics. For coding-savvy students, Python libraries like Torch offer neural networks trained to visualize higher dimensional data, turning algebraic abstractions into colorful. These tools don't just teach, they empower, turning passive learners into active explorers of the cosmic code. The secret sauce, gamification. Apps like HyperRogue drop players into non-Euclidean worlds where walking in a straight line returns you to your starting point, a playful intro to curved spacetime. Meanwhile, 4D Toys by Mark 10 lets users toss hypercubes into higher dimensional gravity wells, their bizarre trajectories illustrating how forces might behave in unseen directions. By framing math as a puzzle to solve rather than a dogma to memorize, these tools ignite curiosity where textbooks often smother it. Yet the most profound resource might be the humblest, storytelling. When a teacher describes our 3D universe as a brain floating in a higher dimensional soup, with gravity leaking like steam from a cup, students don't just understand, they wonder. That's the ultimate goal, not mastery of 30-dimensional calculus, but the spark to keep asking, what if? After all, every breakthrough in physics began with someone refusing to accept that reality ends at the edge of their perception. The quest to unveil string theory's hidden dimensions is accelerating, fueled by tools that would seem like magic just decades ago. Quantum computers, with their ability to simulate subatomic interactions at unimaginable speeds, are now probing manifolds for stable configurations that match our universe's physics. Imagine a machine that doesn't just calculate, but explores higher dimensional landscapes, testing billions of string vibrations in the time it takes to brew coffee. Companies like Google and IBM are already collaborating with physicists, their quantum processors tackling problems like entanglement entropy in holographic models, essentially asking whether the universe's underlying code runs on a two-dimensional surface. Every qubit fluctuation might inch us closer to answering whether extra dimensions are mathematical conveniences or physical realities. Meanwhile, beyond Earth's atmosphere, experiments are escaping the noise of our planet to hunt for dimensional whispers. The Laser Interferometer Space Antenna, LISA, set to launch in the 2030s, will detect gravitational waves at frequencies too low for ground-based observatories. These waves could carry imprints of cosmic strings, hypothetical remnants of the early universe's higher dimensional symmetries, stretching across spacetime like cracks in ice. Even more tantalizing are proposals to repurpose GPS satellites as dark matter detectors. If dark matter particles interact with hidden dimensions, their subtle tugs on atomic clocks in orbit could reveal patterns invisible to terrestrial labs. On the theoretical front, physicists are reimagining the very nature of dimensions. Some models suggest that what we perceive as extra dimensions might not be spatial at all but algebraic, encoded in the relationships between particles, like invisible threads connecting dots on a graph. Others explore fractal dimensions, where spacetime's structure changes depending on the scale you observe, blending the quantum and cosmic into a single geometric tapestry. These ideas aren't just abstract musings, they're frameworks for experiments. The next generation of particle colliders, like the proposed 100-kilometer Future Circular Collider, could smash particles with enough energy to temporarily uncurl dimensions, creating exotic particles that wink in and out of our observable reality. Yet the boldest proposals lie in astronomy. If our universe is floating in a higher dimensional bulk, collisions with neighboring membranes might leave scars in the cosmic microwave background, cold spots or strange polarization patterns that defy conventional explanations. Telescopes like the observatory are scanning these ancient photons for anomalies, treating them as cosmic hieroglyphs waiting to be deciphered. Even black holes, those relentless destroyers of information, could become messengers. Their evaporation via Hawking radiation might encode data about the dimensionality of spacetime, like steam rising from a hidden cauldron. The challenge, of course, is that extra dimensions don't owe us visibility. They might forever linger as mathematical specters, their existence inferred only through indirect clues, like gravity's peculiar weakness or quantum entanglement's spooky connections. But that's the thrill of the hunt. Every null result narrows the possibilities, every anomaly sparks new theories. Whether string theory's dimensions are ultimately confirmed or supplanted by something stranger, their legacy is secure. They've stretched our imagination beyond the limits of perception, teaching us to interrogate reality not just with telescopes and colliders, but with the unyielding power of human curiosity. The next breakthrough might come from a lab, a supercomputer, or a scribbled equation. But wherever it emerges, it'll remind us that the universe's greatest secrets often hide in plain sight, waiting for the right lens to bring them into focus. Critics often dismiss string theory as a beautiful mathematical fantasy, a playground for equations that can't possibly connect to the real world. But this overlooks a crucial truth. The history of physics is littered with ideas that seemed untestable until technology caught up. When predicted gravitational waves in 1916, he assumed we'd never detect them. A century later, LIGO proved him wrong. The real issue is whether string theory is testable. It's how we test it, and whether we're creative enough to look beyond obvious experiments. Take the claim that string theory operates at energies a quadrillion times higher than our colliders can reach. While it's true we can't directly pluck a string the size of a length, their vibrations leave traces everywhere. Think of a piano you can't see. You might still recognize its song from the echoes in the room. For strings, those echoes could be subtle anomalies in particle collisions, like missing energy that slips into extra dimensions, or rare particle decays that defy the standard model. The Large Hadron Collider has already scoured data for these fingerprints, and while no smoking gun has emerged, the search has barely begun. Future colliders, like the proposed 100-kilometer Future Circular Collider, will push energies even closer to the scales where strings might hum audibly. Then there's the myth that string theory is just math. This misunderstands how theoretical physics works. Math isn't decoration, it's the scaffolding of reality. When equations predicted antimatter in 1928, no one had seen a positron. The math led the way. String theory's equations don't just describe higher dimensions, they require them to avoid logical inconsistencies. The same equations also predicted phenomena later observed in black hole thermodynamics, like the exact relationship between entropy and event horizon area. That's not numerology, it's the universe whispering its secrets in a language we're still learning. Another common misconception: that string theory is a single, monolithic idea rather than a vibrant ecosystem of models. Critics fixate on the 10-dimensional superstrings of the 1980s, ignoring breakthroughs like AD-S-CFT duality, which links string theory to observable quantum systems. This duality isn't abstract. It's been used to model quark-gluon plasma in lab experiments, showing how strings can describe real-world physics even when hidden dimensions remain out of reach. Similarly, the holographic principle, born from string theory, is now a toolkit for studying everything from superconductors to neutron stars. Perhaps the most persistent myth is that string theory has failed because it hasn't delivered a eureka moment. But science rarely works that way. Quantum mechanics took decades to move from equations to functional transistors. String theory's timeline isn't exceptional, it's typical for revolutions in fundamental physics. What's often missed is its role as a conceptual bridge, solving puzzles like black hole information loss and guiding the search for quantum gravity. Even if strings themselves evade detection, the theory's insights have already reshaped how we see spacetime, entanglement, and the cosmos's underlying structure. The truth is, string theory's biggest hurdle isn't its complexity, it's our impatience. We live in an era of instant gratification, but the universe reveals itself on its own schedule. Every tool we've built, from gravitational wave detectors to quantum simulators, is another lens trained on those hidden dimensions. Whether the final answer is strings, loops, or something stranger, the journey is teaching us more about reality than we ever imagined. And that's far from just math. It's the slow, thrilling unraveling of existence itself. String theory's vision of vibrating strings dancing through hidden dimensions is dazzling, but it's not the only contender in the quest to unite quantum mechanics and gravity. Enter loop quantum gravity, or LQG, a radical alternative that doesn't just ignore extra dimensions, but shreds the very fabric of spacetime into a web of interconnected loops. Picture the universe not as a smooth continuum, but as a tapestry of tiny, woven threads, each so small that a million could fit inside a single atom. Where string theory adds dimensions, LQG subtracts assumptions, proposing that space itself is quantized, a pixelated reality where not even time flows smoothly, but ticks in discrete jumps. It's a stark departure from string theory's elegance, trading manifolds for spin networks, intricate graphs that encode quantum information at every intersection. The clash between these frameworks isn't just technical, it's philosophical. String theory seeks harmony, weaving gravity and quantum forces into a unified symphony played across higher dimensions. LQG, by contrast, is a rebel. It dismisses dimensions we can't see and rebuilds spacetime from the ground up, like an architect rejecting blueprints to start fresh with quantum Lego blocks. For proponents like Carlo, LQG's appeal lies in its austerity. No hidden dimensions, no supersymmetry, just spacetime's granular structure laid bare. The math reflects this. While string theory's equations resemble a composer's score, LQG's resemble a circuit diagram, with loops representing the smallest possible units of area and volume. Yet both theories share a common enemy, the singularity. Black holes and the Big Bang break physics equations, but LQG offers a startling fix. In its framework, gravity doesn't become infinite at a singularity, it reverses like a spring recoiling. Imagine a collapsing star not as a pit of oblivion but as a cosmic bounce, where spacetime's threads stretch to their limit and then rebound, potentially birthing new universes. It's a vision as poetic as string theory's collisions, yet born from entirely different assumptions. You'll twist, these rivals might not be mutually exclusive. Some theorists like Lee explore string loops, hybrid models where strings evolve on LQG's granular spacetime. Others see both as fragments of a deeper theory, like blind men describing an elephant, one grasping the tail strings, the other the trunk loops. Even the holographic principle born from string theory finds echoes in LQG's network-based geometry, suggesting a convergence in the math beneath the metaphors. Beyond these giants lie like causal dynamical triangulations, which simulate spacetime as a mosaic of tiny triangles, or asymptotically safe gravity, where quantum effects tame infinity without new dimensions. Each path reflects a different bet on reality's bedrock, strings, loops, or something stranger. The stakes, nothing less than the universe's operating system. And while experiments lag behind theory, the race itself is reshaping physics, proving that even in science, the most profound truths often begin with a simple question. What if we've been asking the wrong way all along? Behind every revolutionary idea in physics, there's a human story, a moment of insight, a stubborn refusal to give up, or a collaboration that changed everything. Eade, often called the of his generation, didn't start out as a physicist. He began his academic life studying history and political science, even dabbling in journalism before the elegance of mathematics pulled him into theoretical physics. It's almost poetic. The man who would later unify string theory's disparate branches through M theory initially saw equations as a side interest. His transition from politics to particle physics wasn't just a career shift. It was a testament to the magnetic pull of curiosity. Colleagues describes mind as operating on a different plane, where intuition and rigor blend seamlessly. When he introduced M theory in 1995, it wasn't the result of a single eureka moment, but years of wrestling with contradictions, stitching together 5 competing string theories into a single, 11-dimensional framework. His work didn't just solve problems, it revealed a hidden unity, like finding a master key to a labyrinth others had spent decades mapping. Then there's whose AD-SCFT correspondence became one of string theory's most fertile ideas. Born in Argentina, his journey to rewriting physics began with childhood tinkering, taking apart radios, marveling at how invisible forces could produce sound. That hands-on curiosity evolved into a relentless drive to uncover the universe's blueprints. His breakthrough came from asking a deceptively simple question. What if gravity and quantum mechanics aren't separate puzzles but two sides of the same coin? The answer, sketched in a paper now cited over 20,000 times, proposed a holographic universe where a lower dimensional boundary encodes the information of a higher dimensional reality. It was as if he discovered a cosmic sleight of hand, where the universe's deepest truths might be written in a code we're only beginning to crack. What's striking about his approach isn't just his brilliance but his humility. He often credits collaborations and chance conversations for sparking ideas, reminding us that even the most abstract breakthroughs are rooted in human connection. These stories aren't just footnotes, they're reminders that science, for all its equations, is a profoundly human endeavor. Take the late Joe, who once joked that his greatest contribution to physics might have been a mistake. While working on string theory's implications for black holes, he stumbled upon branes, higher dimensional objects that became central to M theory. At first, he doubted their physical relevance, almost dismissing them as mathematical quirks. But that mistake reshaped our understanding of reality, suggesting our universe might be a membrane floating in a higher dimensional expanse. His willingness to embrace the unexpected, to question his own assumptions, epitomizes the scientific spirit. And let's not forget the unsung heroes, the graduate students burning midnight oil, the postdocs running simulations that never pan out, the theorists whose names don't make textbooks but whose stubborn questions keep the field honest. Science advances not just through genius but through grit, through the collective effort of minds daring to imagine the unimaginable. When you peel back the layers of string theory's equations, you don't just find extra dimensions. You find late-night coffee stains, spirited debates in cramped offices, and moments of sheer wonder that remind us why we explore in the first place. The next time you hear about manifolds or holographic universes, remember, these aren't just concepts. They're the legacy of real people who looked at the cosmos and refused to accept that the story ends with what we can see. You don't need a particle collider or a supercomputer to explore higher dimensions. Your imagination is the most powerful tool you've got. Start with something simple, a cube. In our three-dimensional world, it's easy to visualize 6 square faces meeting at right angles. Now, try picturing its four-dimensional cousin, the Close your eyes and imagine the cube expanding outward in a direction you can't point to, creating 8 cubical faces that fold into each other like a nesting doll with impossible geometry. It's not about seeing it clearly but feeling the mental stretch, like a muscle you never knew you had. This isn't just daydreaming. It's how physicist Carl Sagan first introduced millions to the 4th dimension in his iconic Cosmos series, using an apple passing through flatland as a prop. Take it further with shadows. Grab a flashlight and a piece of paper. A 3D object like a coffee mug casts a 2D shadow, a distorted silhouette. Now flip the script. What if our entire 3D world is the shadow of a 4D object? Every twist of the mug changes its shadow. Every shift in higher dimensions could alter the laws of physics we experience. Dutch artist MC played with this idea in his circle limit prints, where fish shrink and expand as they near the edges, hinting at curved space. Your coffee table can become a lab for dimensional thinking. Just tilt the mug and watch how its shadow warps. For a tactile experiment, try string and scissors. Cut a loop of string and glue the ends to make a circle, a 1D creature's entire world. Now, without ungluing, twist the loop into a figure 8. To the creature, nothing's changed, it's still a closed path, but you've secretly threaded it through a higher dimension. This is how mathematicians visualize dimensions in string theory, tiny, twisted loops hiding in plain sight. Kids can grasp this with a game of dimensional tag, where moving through an extra direction lets you evade capture magically. The real mind-bender, mirror worlds, stand between 2 mirrors facing each other. The infinite reflections receding into the distance aren't just copies, they're a glimpse of how higher dimensions might stack realities. Some string theories suggest parallel universes could exist millimeters away in a 4th spatial dimension, separated by folds we can't perceive. Your bathroom mirror becomes a portal to theoretical physics, no equations required. These exercises aren't just playful, they rewire how you perceive reality. When you next pour water, imagine it's a 4D slipping through our 3D slice, its surface tension bending in ways that defy intuition. Or watch a sunset and ponder, could the colors we see be vibrations of strings in dimensions we'll never see, translated into a palette our brains can process? The universe's deepest truths might not be out of reach. They're hiding in everyday moments, waiting for you to look sideways at the ordinary until it reveals the extraordinary. We've traveled through a universe far stranger than our eyes could ever perceive, from the microscopic vibrations of strings to the sprawling landscapes of 30 hidden dimensions. Along the way, we've seen how black holes might be knots in higher dimensional space, how gravity's weakness could be a cosmic illusion, and how our entire reality might be a holographic projection from the edge of existence. String theory's boldest ideas aren't just equations on a chalkboard. They're invitations to rethink everything we thought we knew about time, matter, and the very fabric of reality. Yet for all its brilliance, string theory remains a work in progress, a map still missing some crucial landmarks. The lack of experimental proof frustrates some, but history teaches us that great ideas often outpace the tools to confirm them. Think of gravitational waves, predicted in 1916 but not detected until a century later. Or the boson, theorized in the 1960s but found only in 2012. The universe reveals its secrets on its own schedule, and the absence of evidence today isn't evidence of absence. What makes string theory extraordinary isn't just its potential to unify physics, it's the way it reshapes our imagination. Before space and time were rigid absolutes, before quantum mechanics, particles were tiny balls. Now we're standing at the next frontier, learning to see the cosmos not as a static stage but as a dynamic, multidimensional symphony. Even if future experiments force us to abandon strings, the journey will have been worth it. Like explorers charting unknown territories, theorists have expanded the map of what's possible, revealing hidden connections between black holes and quantum entanglement, between holograms and dark energy. The real lesson here isn't about extra dimensions, it's about curiosity. Every great leap in science began with someone asking, what if? What if space isn't flat? What if time isn't universal? What if our universe is just one page in an infinite cosmic library? String theory reminds us that reality is always richer, weirder, and more wondrous than it seems. So keep questioning, keep wondering, and stay open to the impossible. Because the next dimension, or the next revolutionary idea, might be hiding in plain sight, waiting for the right mind to uncover it. What do you think? Are hidden dimensions the key to the cosmos, or just a beautiful detour? Drop your thoughts below, and let's keep the conversation going. After all, the greatest discoveries start with a conversation, and who knows where this one